wearables. All right, so what are we missing here, and what can we do better? So first, starting with some facts. 30% of users abandon smartwatches over time because of like motivational loss, routine disruption, perceived measurement inaccuracy, discomfort, and battery charging. And about 70% of CGM users experience a skin complication. Then in a large clinical trial of the Zio ECG patch by older adults over a 2-week period, 38% reported itching, 9% indicated hindrance to daily activities, and 1% discontinued the study because of skin intolerance. So this means, wearables need to be made better. So we need to improve user experience. We need to improve our measurement in accuracy. So there are gaps in measurement capabilities. The most popular smartwatches or rings use the wrist or the finger, but we need to know, and it's clear, there are not many parameters that we can measure on the wrist or the finger. So for example, skin temperature, measured on the extremities correlated poorly with core body temperature and is susceptible to, ambient temperature fluctuations. And that's something, Kavi and Zach are working on. Then there's also, for example, if we want to measure high quality, respiratory signals such as tidal volume, effort, and obstruction, they're not going to be measured on the wrist or finger. So I don't know how to measure respiratory signals on the wrist or finger. So, and then there are a lot of common clinical measurements not well served by mainstream wearables, such as EEG or EOG. EOG is the electrical activity of the eyes. There's no wearable to measure EOG. And, we have brain oxygenation, motion kinematics, continuous blood pressure, advanced hemodynamics, such as cardiac output, stroke volume, and systemic vascular resistance. Then we have tidal carbon dioxide, arterial tonometry, blood chemistries. We do blood works all the time, and inflammatory markers such as cytokines. So these are all measurements that are done regularly in clinics, but these are not served by wearables. So wearables need to improve. There are also parameters not currently used in clinical practice, but they hold potential value, such as vocal biomarkers. We use a MA sensor to record our voice. Then we can analyze our voice. We can see emotional well-being, social isolation, cognitive decline. So and another example is swallowing activity and dynamics. So swallowing is rarely quantified and never measured continuously in standard clinical practice, but they can indicate stroke, Parkinson's, and Alzheimer's disease. So, and also skin properties such as hydration, elasticity, or near surface flow that we can measure using our thermal sensor. These are all not currently being used in standard clinical practice, but they hold potential. Then there's also gaps in form factors. So there's a fundamental mismatch between electronics and the skin. We know that electronics is planar, rigid, and physically static, but human body is soft and dynamic. Our skin naturally stretches, bends, and flexes. And from routine daily activities, what that means is that our device will easily detach from the skin. So we need to use a fixation methods like tapes, straps. These cause skin complications, and they are not conductive for long-term wear beyond 1 to 2 weeks. So we need devices that are imperceptible to the body. So we need to make devices smaller, lighter. We need to eliminate the use of tapes And, once we get there, we may be able to mount our devices on many different body parts to measure more parameters. And this will require fundamental